Thank you, and good evening everybody in Herefordshire. This is the end of everything. As you can see from the subtitle, I'm going to be talking about the fate of the Earth, the fate of the Sun and the solar system, the fate of the galaxy, and ultimately the fate of the universe. So you could say this is effectively to eternity and beyond. So I'll give a little bit of a prologue before jumping into the future of the Earth, the Sun and the solar system, and then looking further into the future for the future of stars and galaxies, and then into the far, 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 far future to think about the ultimate fate of the universe. And then, to avoid leaving you on a really depressing note, I'll have a very quick epilogue at the end. So I'm not going to be talking about how the universe came to be, but just to sort of put it in perspective, a reminder that the universe came into existence something like 13.8 billion years ago. And the universe that we see today, the observable universe, all 100 billion light years of it or so, used to be a lot closer together. We know the universe is expanding, and the current observable universe used to be a lot smaller. In fact, it used to fit in the volume of a golf ball. That's going back an awful long way. But ever since then, the universe has been expanding and cooling, and the universe made lots of protons and neutrons, which led to a lot of hydrogen and some helium. When the universe eventually turned transparent, it released the light that was bombing around at the time, and that's the cosmic microwave background radiation that we see today. So that's 13.8 billion years in just a few seconds. That just paints the picture of where we are now. But what I'm talking about, of course, is where we're going from this point onwards. We know the universe is full of stars and galaxies, but what's going to happen to all of these things? And on a slightly more parochial scale, what's going to happen to the Earth on a shorter time scale than what's going to happen to the rest of the universe. To try and keep track of where we are, I'm going to use this timeline along the top of the screen there. Each small box represents 10 times further into the future than the previous. So in other words, I'm going to be talking about 10 years into the future, 100 years, 1,000 years. Well, actually, I'm not going to spend very long on the very short time scales. I'm going to start at around about 1,000 years into the future and then move on. 10 to the 4 years, 10 to the 5, a million years into the future, 7, 8, 9, a billion years into the future, 10, 11, 12, a trillion years into the future. That's not where it's going to stop, but that's a convenient way of displaying what's going to be happening on this sort of time scale. Before I move on, let me credit the fact that a particular publication by Adams and Laughlin, I use this publication referenced at the bottom of the screen there, because they talk about the timescales on which various astrophysical phenomena are likely to occur. And I used that paper to try and get my slides in the right order. So I'm not necessarily going to be talking about the Earth and the Sun and the galaxy. I'm going to be talking about various events, and I'm going to try to put them in a strict time order in terms of a temporal sequence. So some things might jump around a little bit, but it will always be progression from left to right, meaning further and further into the future. So I'm not going to talk about 10 years or 100 years. Let's work on the assumption that we get our act together and we get fossil fuel under control and we don't have too many nuclear wars such that we're still in existence from 1,000 years onwards. 1,000 years into the future, the Earth will be rotating more slowly than it does now. In a separate talk, I talk about why the Earth is slowing down because of the way the Moon is pulling on the Earth. And at the moment, because the Earth is slowing down, and we've noticed it slowing down since the invention of atomic clocks more than 50 years ago, but because the Earth is slowing down and we want to keep our clocks synchronized, at the moment we add a leap second every few years. But in the future, 1,000 years into the future, the Earth will have slowed enough that instead of adding a leap second every few years, we will need to add a leap second every few weeks. Now that's not particularly a problem, it's really just an inconvenience. Moving forward into the future, it might well be that locally some supernova goes off, which might be spectacular for amateurs, it might conceivably be dangerous if it's close enough to us. But we can't really talk about the timescale on which these are going to occur. All we can talk about is the likelihood of a particular star perhaps coming to the end of its life. So we can't talk with any certainty as to what's going to happen in, let's say, 10,000 years' time. But we can talk about what's happening to the Earth in the same timescale of 10,000 years or so. We know how the Earth is moving, both the way it's rotating and the way it's going round the Sun. And one of the aspects of the Earth's change is precession. As you can see from this little graphic on the left-hand side, the direction in which the Earth's axis is pointing changes on a cycle of some 26,000 years. And that means the pole star will change. We can map out the circle, the direction in which the pole is pointing, and at the moment the pole is pointing close to the star Polaris, which is convenient for finding north. But in another 12,000 years or so, the pole will be pointing, if you like, on the opposite side of its tilt, and it will be close to the star Vega. So we'll have a very bright pole star. Won't be quite as close as Polaris is to the pole, but it'll be very easy to find north. But apart from that, making life for Boy Scouts rather easier, what's the consequence of the Earth's axis pointing in a different direction in the future? Well, one of the consequences, when we think about the direction of the Earth's axis relative to the elliptical orbit around the Sun, at the moment the Earth is closer to the Sun, i.e. at perihelion, during northern winter. And remember, most continents and most of the population of Earth are in the northern hemisphere. So at the moment we are closer to the Sun when we have northern winter, which tends to mitigate some of the temperature changes. But if the Earth's axis is pointing the other way towards Vega, that means we'll be nearer to the Sun during northern summer, which means being closer to the Sun and being tilted towards the Sun, it means the seasons will be a little more dramatic, a little more exaggerated. So variations in the Earth's climate we know are coming in the future, regardless of man-made influence on the Earth's climate. And these natural variations that are due to changes in the Earth's spin or changes in the Earth's orbit around the Sun are manifestations of what we call Milankovitch cycles. And I'll mention that again in a little while. Moving forward 10 to the 5 years into the future, at this point the Voyager spacecraft are likely to pass by some nearby stars. In the 1970s, Voyager 1 and Voyager 2 were launched past Jupiter-Saturn and Jupiter-Saturn-Uranus-Neptune, and they are now on their way out of the solar system. It'll take quite a while for them to reach the nearest star, 10 to 100,000 years or so. If we look at the directions they're heading, here we've plotted the Voyager as well as the Pioneer space probes. At the top, Voyager 1 on this timescale is going to pass close to the star Gliese 445. And at the bottom of the screen, Voyager 2 is going to pass close to the star Ross 248. Also on this particular graphic are Pioneer 10 and Pioneer 11. They were launched earlier than the Voyagers, but they were travelling more slowly, so they will take a little longer to reach nearby stars. Pioneer 10 is on the way towards Aldebaran, and Pioneer 11, travelling in the opposite direction, is heading towards the galactic centre. More about the Voyagers later. On the same timescale of about 100,000 years or so, it is fairly certain that the Earth will go through another ice age. Looking at the historical records, we see that glacial and interglacial periods tend to occur on timescales of order 100,000 years. And given that we've only recently entered one of the warm phases, the so-called interglacial phases, it looks like the next ice age is due on the timescale of order 100,000 years. We survived the last one, so presumably we're quite capable of surviving the next one, but we do have to think about how we're going to manage in a much colder Earth. These variations that occur on timescales of 100,000 years are related to the Earth's orbit, and again, it's another manifestation of the so-called Milankovitch cycles. In 100,000 years, the Earth will have slowed down even further because of the gravitational tug of the Moon. In 100,000 years, leap seconds wouldn't need to be added every year, they would need to be added every day to keep our clocks synchronized. In other words, in 100,000 years, the rotation period of the Earth will be somewhere in the vicinity, not of 24 hours, but 24 hours and 1 second. So perhaps the easiest thing to do would simply define 1 minute within the day as lasting 61 seconds rather than 60 seconds, and that will keep our clocks synchronized for a little while. But the Earth will continue to slow down in years to come. On a timescale again of 100,000 years, it is thought that Eta Carina, a very large unstable star in the southern hemisphere, is quite likely to go into a supernova phase. We can't be absolutely sure, but if we look at current images of it, as shown here by a Hubble Space Telescope image published by the Astronomy Picture of the Day team back in 2019, we see that this particular star has already shrugged off its outer layers to produce this planetary nebula. And any star that's so unstable that it can't hang on to some of its outer layers is surely a candidate for being a supernova before too long. So we can't be sure, but it's likely that within 100,000 years or so, Eta Carina could be one of the most spectacular supernovas that would be visible from Earth. This is not quite an artist's impression, but almost. This is a real image of the night sky with an observatory in the foreground here, taken by an amateur astronomer. But in this particular case, the image has been modified, shall we say, doctored, if you wish, to show what the night sky might look like if Betelgeuse goes supernova, which is thought to occur perhaps on the same sort of timescale. So it will produce a spectacular bright light in the nighttime and probably the daytime sky, but of course it's going to completely wreck the constellation of Orion. So there's, swings and roundabouts. We gain, but we lose. Again, we can't be sure of the timescale, but it's thought that Betelgeuse is unlikely to survive another 1,000,000 years, so perhaps of order 10 to the 5 years is its predicted lifetime. But it's not just supernova we have to worry about. There are other rather dangerous stars out there. For instance, Wolf-Rayet 104, it might be 7,000 light years away. That sounds like a great distance. Betelgeuse, for instance, is only some 600 or so light years, but this is 7,000 light years away. Surely that's far enough that we can't possibly be in danger if this particular star explodes. Well, the death of this star might produce a radiation burst that's even more powerful than a supernova if we happen to be lined up with one of these jets that appear to be coming from the region of the star. The rapid rotation of this stellar system produces these jets in a way that perhaps we don't fully understand. But it is possible that if one of these jets happens to be pointing towards Earth, then the radiation released on its death could be a danger to life on Earth. That would require the jet to be quite accurately aligned with Earth, but at the moment it's very difficult to tell whether the jet is pointing in our direction or not. So it's something to bear in mind. It's not only supernova that could cause a problem for us, other stars at greater distances could also be a problem. When observed at great distances, these stars are often called gamma-ray bursts. If we move forward to 1,000,000 years into the future, we know that a star is going to pass close by the solar system. All of the stars are going round in independent orbits around the centre of the Milky Way. But because we're all in slightly different orbits, every once in a while the Sun and the solar system will come close to one of its neighbours. They will drift together and then drift apart again. And it's been calculated that in about 1,000,000 years, Gliese 710 will actually pass close by and then disappear again. It'll come close enough to actually enter the Oort cloud, this cloud of perhaps trillions of small objects, some of which are going to be disrupted by the passage of another star entering our solar system. And almost certainly that's going to produce a whole load of objects raining down from the Oort cloud into the inner solar system. It's been estimated that it could result in, for instance, naked eye comets within the inner solar system every month for 1,000,000 years. So it's going to be quite spectacular, but we're going to have to wait 1,000,000 years or so for the start of this onslaught. One thing to note is that for a little while, our solar system will have 2 suns, just like other systems you might have heard about. Also on the timescale of about 1 million years, here I show a picture of meteor crater. Perhaps you've seen this before. I'm showing it perhaps not for the reason you think. I'm not claiming that an impact of meteor crater will occur every 1 million years or so. I'm showing this for 2 reasons. One, isn't it quite amazing the fact that this particular impact just missed the visitors centre? What a stroke of luck that was. But no, the main reason for showing this image is that on a timescale of 1 million years or so, we would expect weathering events to remove any evidence of impacts. So for instance, this meteor crater in Arizona, it's only some tens of thousands of years old. If it was 1 million years old, we probably wouldn't see it because the weathering, the wind and the rain, would actually reduce the visibility of an impact crater like this. You could say, well, yes, that's true of the Earth, but it's not true of other objects. For instance, the moon, things will last forever on the moon because there's no weathering. Well, not strictly true. If you look at what's going on the moon, it's constantly bombarded with micrometeorites. They are effectively pulverizing the surface of the moon. So the footprint of Aldrin there will last for quite a while, but it won't last forever. It's been estimated that in 1 million years or so, the micrometeorite impacts will probably remove things like footprints. And eventually, all evidence of the Apollo landings will be erased because basically all of the hardware that's left there will disintegrate under the impact of long-term micrometeorite impact. Let's move forward to 10 million years into the future, and we're back with the space probes, this time Pioneer 10. Pioneer 10 and 11 had plaques on them indicating where they came from. So the spacecraft will probably pass other stars on timescales of order 100,000 years. So on a timescale of 10 to the 7 years, it will have passed perhaps hundreds of different star systems. It might have passed through hundreds of solar systems. And this plaque will tell anybody that finds the probe where the probe came from. The little picture at the bottom is a schematic that we come from the third rock from the Sun, and the image on the left-hand side is an indication of a pulsar map that tells it if you can find these pulsars, then you can work out, roughly speaking, where we came from. I'm showing this at the point of 10 to the 7 years because after that length of time, the plaque will be so pitted with micrometeorites or impacts with dust and other things that it will essentially be unreadable. Space is not empty. Interstellar space is not empty. It's full of the so-called interstellar medium. It's full of gas and dust. And after 10 million years or so, all of the impacts will probably make that plaque unreadable. So if Pioneer does get caught or captured or looked at by extraterrestrials after this sort of timescale, then unfortunately they might still be able to determine that Pioneer 10 is an extraterrestrial spacecraft, but they won't necessarily be able to tell where it came from due to the inability to read the plaques any longer. Let's move forward to 100 million years and think about Saturn's rings. But before we think about what's going to happen to Saturn's rings, let's just ask ourselves where they came from in the first place. It is thought that perhaps the destruction of one of the moons of Saturn gave rise to Saturn's rings. And when we look at the moon Mimas or Mimas, we might look at that and think to ourselves,
that's no moon, it's a space station.
Because it does bear a certain resemblance to the Death Star, everybody has to admit. But simulations have been done to try and indicate if you did pulverize one of the smaller moons of Saturn, can you actually generate the rings? And this simulation shows what would happen if one moon is smashed by collision, let's say, with a comet and completely pulverized. What would happen to the debris? And perhaps it's quite surprising that it doesn't take long for the debris to form a ring system. Notice that in only a matter of hours, the debris surrounds the planet, and in only a few weeks, it's formed what you can recognize as a ring system. So it might only take a few weeks to make a set of rings by taking a moon and crushing it up into dust and letting it distribute itself around the planet. But because of the interaction of all the particles, they will slowly drift in towards the surface of Saturn itself. In other words, the ring material is slowly raining down on the surface of Saturn. So it's taken millions of years for the debris to migrate inwards from that original simulation into the rings that we currently know and love. But the point is, on a timescale of many millions of years, this process will continue. So if it's taken millions of years from the original impact to form the rings, then on a timescale of perhaps 100 million years or so, all of the ring material that we can currently see will again migrate inwards and will rain down on the surface of Saturn to the point where essentially there will be nothing left to see. So a sad day will come when Saturn no longer has its rings. On a same sort of timescale of 100 million years or so, we have to remember that the solar system is not quite as clockwork as an orrery or a tellurian would have us believe. We look at these wonderful clockwork type things and we think about the planets going around the sun, and we look at, I don't know, an app like Stellarium, which tells us where the planets are now, and if we wish, where the planets were 2,000 years ago, to try and work out what the Star of Bethlehem was, for instance, and we can work out where the planets are going to be thousands of years into the future. But we can't do that on timescales of hundreds of millions of years. On a timescale of 10 to the 8 years, the solar system is not clockwork. The solar system is chaotic. And we don't even know how many planets there will be in the solar system. We don't know what the ordering of planets will be, and we don't know if all the planets we see today will still be present. In the past, we think the solar system was originally made with the planets in a different order to which we see them now, and they have swapped orbits on a timescale of billions of years. And that is likely to happen again. So because of chaos, because of the lack of predictability of complex systems, we can only talk about the predictability of where things are going to be on timescales of perhaps millions of years, but not on timescales of 10 to the 8 or hundreds of millions of years. On that same timescale of 10 to the 8, 100 million years or so, if we think of our position in the Milky Way at present, we are currently between spiral arms on a so-called spiral arm spur. So in other words, the relative concentration of stars around us is relatively low compared to the average within the Milky Way. Stars will rotate around the Milky Way on a timescale of order hundreds of millions of years. And as the Milky Way rotates, the Sun is going to move from a relatively low density region in between two spiral arms into a higher density region of a spiral arm itself. And that means we are going to have, on this timescale, a lot more stellar neighbours because we're simply moving into a more densely packed region of the Milky Way. So what's the impact of being in an environment where we have more stellar neighbours? Well, there's at least two impacts which could make a difference to the Earth. The first is, if we've got more stellar neighbours, just like Gliese 710, more stellar neighbours means more disruption to the Oort cloud, which means more rocks coming our way. If we have a look at extinction level events of the past, we see this spiky sort of curve, and over hundreds of millions of years we see a number of specific spikes where a lot of species went extinct. The most recent one, the KT boundary, the Cretaceous Tertiary boundary, that's the one that killed the dinosaurs. And you can see that there tends to be, very roughly, a sort of period of order 100 million years or so where these spikes keep coming back. And it is thought that it is the motion of the solar system around the Milky Way that actually gives rise to these variations where there are certain periods in history where we are much more likely to be hit by rocks coming in from the Oort cloud. So here's an artist's impression of what that might look like. A large lump of rock heading for, well, if we have a look on the left-hand side, it seems to be heading for Italy, according to that outline there. Okay, bad news for Italy, but of course, if it's a large rock, it'll be bad news for the rest of the Earth as well, as it churns up a huge amount of material, regardless of whether it hits water or hits land. When one of these rocks hits us, species will be exterminated. The only real question is, will that include us? And of course, the recent DART mission was trying to establish whether or not, if we find there's a particular rock heading our way, what are the chances that we can do something about it by changing its orbit early enough to push a particular asteroid away from impact of Earth such that it misses the Earth. We've got 100 million years to work this out, so it's not too much of a panic. DART is the first stage in a long line of experimental missions trying to establish whether or not we can avert this sort of disaster. Also, on a timescale of order 100 million years or so, we have to watch out for nearby supernova. So not only will having more stellar neighbours mean that we're more likely to get rocks thrown our way because of perturbations of nearby stars, but if we have a lot more nearby stars, it's more likely that one of them could go supernova at some point. A supernova within 100 light years of Earth could be a danger. A supernova within 20 light years of Earth might conceivably end all life on Earth if we are that close. At the moment, there are no supernova candidates that close to us. But in 100 million years, when we are in a spiral arm of the galaxy with a lot more neighbours, perhaps we might have a neighbour which is a supergiant or very massive star which will go supernova at the end of its life. So it's something we have to be aware of. Certainly it's happened before. If we look at the historical record, we find evidence that there have been supernova within 100 light years of the Earth in the past. When a star goes supernova, it generates an isotope called iron-60, and that doesn't occur naturally on Earth. And iron-60 has indeed been found in Earth sediments. Now, iron-60 is a nucleus with a half-life of a few million years, which means over a period of a few million years, iron-60 will change into different elements. It'll change into cobalt-60 and then very quickly into nickel-60. That means if you find any iron-60 on the Earth, it can't have been there for billions of years, because if it was there right at the start of the Earth's creation, it would already have changed into something else. So if you find any iron-60 in the Earth, it must have arrived relatively recently. And that's how we know that supernova must have gone off within a certain distance of the Earth in recent history, meaning not that many millions of years. So we know it's happened, and we think it is likely to happen again, especially when we go through another spiral arm of the galaxy. Coming back to our old friend, the Earth's rotation, in 100 million years, the Moon will have had an awful long time to tug at the Earth. Tidal friction means that the Moon will continue to rob the Earth of some of its angular momentum. It'll slow the spin of the Earth and push the Moon into a larger orbit. On a timescale of 100 million years or so, the length of the day, because of the slowing of the Earth, is now about 25 hours. It's now crazy to start talking about leap seconds getting added to keep our clocks synchronized. At some point, we'll have to just give up on a 24-hour day and say, let's change to a 25-hour day, or a 26-hour day, or a 27-hour day. But as well as being a problem for our clocks, there is another consequence. As well as the Earth slowing down, the Moon is getting further away from the Earth. And it won't be long before the distance from the Earth to the Moon is so large that it will be impossible for the disk of the Moon to cover the disk of the Sun. In other words, at this point, approximately a billion years from now, there will be no more total eclipses of the Sun. The best we can hope for is, like the image on the right from Astronomy Picture of the Day in 2020, we will still get annular eclipses because the disk of the Moon will not be large enough because of its distance to cover the disk of the Sun. So we will still get annular eclipses, but we will never get a total eclipse of the Sun ever again beyond this point. A bit of a shame. So those that like solar eclipses, get your eclipse chasing done now. You've only got a billion years before you won't have any more opportunities. But there's another even more important aspect for the Moon moving away from the Earth. The moon has a stabilizing influence on the tilt of the Earth. At the moment, the tilt of the Earth, otherwise known as the obliquity, is about 23.5 degrees. And from historical records, we can work out that that hasn't really changed much. It's changed by perhaps 1 degree either side of the average value of about the current value, 23.5 degrees. If we look at the little graphic on the left-hand side, you can see what that means. It's only a tiny change to the tilt of the Earth, which of course will then influence the seasons of the Earth. But if the moon is too far away, it finds it difficult to influence the tilt of the Earth. For instance, if the moon was 25% further away, then the tilt of the Earth could change erratically. It would no longer be stabilized by gravitational influences of the moon. And if the tilt of the Earth changes erratically, then we get wild variations in the Earth's climate. Far, far more dramatic than any of the global warming changes that we're talking about in the next 100 years or so. So that's something that we have to watch out for. In 1 billion years, the Earth's climate is definitely going to change, and it could change in a totally unpredictable way because we no longer have the stability of a large moon close by, keeping us at a nice stable 23 degrees to the ecliptic. Still on a timescale of 1 billion years, let's return to the probes that we've sent out of the solar system. Remember, I talked about the Pioneer probes. After 10 to the 7 years or so, the Pioneer plaques on the probes themselves will be unreadable because of the pitting or the erosion produced by flying through the interstellar medium for tens of millions of years. So how come the Voyager disks are expected to last 10 to the 9 years? The Voyager disks are these gold-plated disks on the right-hand side with recordings of people and music and sounds of the Earth. The reason these disks are thought to survive for 1 billion years rather than simply 10 to the 7 years or so is because the disk itself is sitting under a protective cover, which is shown on the left-hand side. So the good news is that Voyager can fly through thousands upon thousands of different solar systems in the hope of somebody perhaps picking it up and realizing that Voyager is an an alien spacecraft, and then working out that this has been sent from a particular species and listening to this record to get these welcome messages from Earth. The catch is that after 1 billion years, the record itself will still probably be in reasonable condition because of the protection of the cover on the left-hand side. However, the cover on the left-hand side will get pitted and eroded, and it's the cover that contains the instructions for how to read the record. So after 1 billion years, the record might survive, but any alien species that pick it up, any of the thousands of solar systems that this particular Voyager will pass through, any of them picking it up might be able to see that the record has survived, but unfortunately will not know how to play it in order to hear the sounds of Earth. That'll be a bit of an irony, won't it? Still on a timescale of order billions of years into the future, the sun will start to change. The sun will start to run out of its hydrogen fuel and will start to go into its red giant phase. As it starts its journey into the red giant phase, the sun's luminosity will increase by something of order 10% for every billion years from this point onwards. And the increase in luminosity will drive the Earth into a greenhouse effect. And at the point of a few billion years, the surface temperature of the Earth will probably be of order 80 Celsius. It's not altogether obvious how we could possibly survive that. Given how long this is going to last, we can't simply go underground and hope to survive. At this point, I think we'd have to declare the Earth uninhabitable and go and find another planet to live on. At this temperature, the oceans will evaporate, as well as the surface temperature being a little bit on the uncomfortable side. As the sun expands into a red giant phase, it will expand and the surface of the sun will get closer and closer to Earth. And so you can imagine the scale of the sun compared to the scale of the Earth. If the surface of the sun does get close to the Earth, you can appreciate that this could be a little bit of a problem for us. And it's often been said that as the sun expands into a red giant, it will engulf the Earth's orbit. That's probably true. It's also sometimes said that the sun will engulf the Earth. Well, that's not necessarily true, because when you work out what's going to happen, as the sun expands, there will be very strong solar winds from the sun as it goes into the red giant phase, which means the sun will actually lose mass as it comes to the end of its life. If it loses mass, there's less gravity pulling on the Earth, which means the Earth's orbit is going to increase. So this little cartoon on the left shows that as the sun gets larger, the Earth actually moves away from its original position. So yes, the sun will expand and will probably end up engulfing the original Earth orbit. But in the meantime, the Earth will have moved away into a new orbit. So it's likely that the Earth will never get engulfed by the sun. It'll certainly get hot, but it won't get engulfed. Some people think the Earth might survive. It's not obvious that humans can, but the Earth might survive the end of the sun's life. When we get to many billions of years, approaching 10 to the 10 years, after the sun has gone through its red giant phase, it will slough off its outer layers, it'll generate a planetary nebula, and the core left behind is a white dwarf, a small object approximately the size of the Earth, made essentially of carbon. And if the pressures and temperatures are high enough in the core of a carbon star like this, perhaps the inside of the white dwarf might be a very large diamond, but that's rather speculative. If the Earth does survive, there are more problems ahead, because on a timescale of many billions of years, regardless of what happens to the sun, expanding into a red giant and then ending its life as a white dwarf, the Earth's core is going to cool. The Earth's core is not heated by the sun or any solar process as such. The Earth's core is heated by radioactive decay of elements that have existed for billions of years. But eventually that radioactive decay will not be enough to keep the core of the Earth molten. And when the core of the Earth solidifies, it will lose its magnetic field. And if it loses its magnetic field, that means the Earth will be exposed to radiation from the sun and, more importantly, from cosmic ray sources. It is thought that perhaps Mars lost its magnetic field in the early part of its evolution. Mars is a much smaller planet. Its core would have cooled sooner, and if its core cooled and solidified, Mars would have lost its magnetic field fairly early on, and without a protective magnetic field, then perhaps that was one of the contributing factors to the fact that its atmosphere has been stripped away, or at least very much thinner than, for instance, the Earth's atmosphere. So the Earth had to contend with its host star getting larger and then smaller. It's had to contend with the loss of a magnetic field, and also one other event on the same timescale looks like an absolute disaster, and that is the Milky Way is going to collide with the Andromeda galaxy on the same timescale of order a few billion years or so. This is an artist's impression of what it might look like as seen from Earth, assuming Earth survives, as the Andromeda galaxy comes towards us in a few billion years. It'll be very large in our sky, and at about 4 billion years into the future, the two galaxies will start to merge together, and there will be an absolute riot of new star formation. When one galaxy passes through another, it's unlikely the stars will collide. The sun probably will not hit another object, and if the planets are still going round the sun, they will continue to go round the sun in all probability. Even if the sun gets ripped out of the Milky Way galaxy, the planets will probably go with it. So the two galaxies are going to pass through each other, and then they will settle down into one mega galaxy, perhaps with two supermassive black holes at the centre, the original supermassive black holes from the centre of the Milky Way and one from the centre of Andromeda. Eventually, far enough into the future, those two black holes will merge into one as well. So although it sounds dramatic, the collision of two galaxies is probably the least of the Earth's concerns, in that it won't necessarily have any direct impact on what the Earth and the Sun are doing. If we look forward to 10 to the 11 years, this picture looks like a little bit of a Photoshop. In fact, it's a genuine picture of the full moon and the Earth as seen from the Deep Space Climate Observatory. But at this point, the tug of war between the moon and the Earth, the exchange of angular momentum will stop. Because at this point, one day will be 1 month. In other words, the length of time it takes the Earth to spin once on its axis will be the same as the length of time it takes the moon to do one orbit of the Earth. So that means that the Earth will be tidally locked to the moon, just like the moon has been tidally locked to the Earth. One side of the Earth will now always face the moon, just like a mirror image of what the moon has been doing for billions of years, because of course the moon always shows one face to the Earth. Well, eventually the Earth will always show one face to the moon. That means from any point on the Earth, depending on where you are, you might be on a continent in which you always see the moon in the sky. It doesn't rise, it doesn't set. And there will be half of the Earth in which you will never see the moon because it will never rise above your horizon. Again, whether humans are around to experience this, well, we don't know, but it is almost certain that the tidal locking of the Earth to the moon will occur on these sorts of timescales. If we push this red box as far as we can go to 10 to the 12, so we're now talking about 1 trillion years into the future. If we look at the galaxies around the Milky Way has a lot of small galaxies around it at the moment, and the local group comprises the Milky Way and its satellites, plus the Andromeda Galaxy M31 and the Triangulum Galaxy M33. We've already seen that the Milky Way and Andromeda, the two most massive galaxies, are going to merge, but eventually, on these timescales of order 1 trillion years, all of the objects in the local group, the 3 big galaxies plus these dozens, if not hundreds, of smaller galaxies, are all going to end up as one mega galaxy. In other words, there's going to be a cannibalistic attitude of these galaxies, and all of them are going to end up in one. But what are we going to see for galaxies beyond our own local group? Well, even if the galaxies are receding from us faster than the speed of light, and the expansion of the universe is quite definitely taking some galaxies away from us faster than the speed of light. I tried imaging one of these a couple of years ago during a lockdown challenge. I imaged a galaxy without using a telescope, and this galaxy was receding from us at more than twice the speed of light. So we know that even if the universe is expanding, even if galaxies are moving away at superluminal speeds, we can still image them. And if we look at, for instance, the image on the right, the Hubble Ultra Deep Field, there are thousands of galaxies. And quite a few of those galaxies will be receding from us faster than the speed of light. But because the expansion of the universe is going to continue, and if we're looking this far into the future, 1 trillion years into the future, there will come a time when the galaxies are so far apart, we will not be able to observe galaxies outside our own. So it's quite sobering to realise that if a civilization comes into existence, let's say, of order 10 to the 12 years from now, if they build themselves a Hubble Space Telescope and they try and take a Hubble Ultra Deep Field, what they will see is essentially nothing other than the stars in their own galaxy. Those will still be visible, but they will not be able to see anything beyond their own galaxy. A civilization that comes into existence at this sort of time in the universe will not be aware of the fact that the universe is full of galaxies, full of trillions of galaxies. As a bare minimum. They will only be aware of the stars and the other objects within their own galaxy. Doesn't matter how big a telescope they build, they will not be able to see galaxies simply because the expansion of the universe will be taking those galaxies away too fast. The universe is going to run out of hydrogen. I said when I mentioned this other talk, which I'm not giving you here, the beginning of everything, when we look back to how the universe came to be 13.8 billion years ago, we know, or at least we've got a pretty good idea, that it took about 3 minutes to make all of the hydrogen in the universe. That's what has been making stars for billions of years and will continue to make stars for many, many, many billions of years into the future. 3 minutes to make it all, but it won't last forever. After 1 trillion years or so, it'll be nearly all gone. And so new star formation is going to be severely hampered if the basic fuel source is running out. As an aside, some people think and hypothesize that, well, if there isn't hydrogen to make stars, is it possible you can make stars out of something else? Well, it's not obvious that you can do that, but it might be possible for stars to form from gas having much heavier proportion, much greater proportion of heavier elements. Instead of starting with hydrogen, is it possible you could start with a whole load of carbon or silicon and make stars with much heavier elements? It is hypothesized that if you do that, it might be possible to make a star in which nuclear reactions are occurring at the core, but the surface temperature is amazingly low. So for a red giant, its surface temperature might only be a few thousand Kelvin, but it's been hypothesized that maybe you can make stars in which nuclear reactions are occurring at the core, but the surface temperature is perhaps only hundreds of Kelvin. Perhaps even only 0 Celsius, at which point ice might form at the surface of the star. Frozen stars. And for those of you who think I'm talking about the Disney version of frozen stars, if that's the picture you've got in your head, let it go, because what I'm talking about is stars in which we've got nuclear reactions at the core, but ice at the surface of the star. A pretty amazing idea. Still only a hypothesis, but quite an incredible idea nonetheless. But before we go any further, and yes, we've reached 1 trillion years, but that's not endgame, that's not the end of time, that's a long way into the future, but we're not quite there yet. Before we go any further into the future, we need to consider what the expansion of the universe looks like. So here's an idea of what might happen to the universe in terms of its relative size on the vertical axis as a function of time. And that's where we are now, 13.8 billion years after the Big Bang, or thereabouts. And its relative size is 1. So if we go backwards in time, we see the universe had essentially 0 size at a point we call the Big Bang, but notice that the Big Bang occurred at possibly different times depending on which of these coloured lines is the correct coloured line that we should be looking at. We don't really know which is the correct coloured line because each of those coloured lines represents how much mass is there in the universe. If we could answer that question, then we could figure out which line we are actually on. So for instance, if there was a huge amount of mass in the universe, then we would follow the orange line. From where we are now, the universe would get larger for billions of years, but with a very large amount of mass in the universe, gravity would take hold and the universe would start getting smaller again. And eventually we'd end up with a big crunch when the universe collapsed in on itself. That would be a so-called closed universe. But to the best of our knowledge, that's not the universe we live in. Of all the possibilities that exist, we think the best guess is the fact that we're living in a universe in which the matter and energy content of the universe put us on the red line. In other words, when we look at where that red line is going into the future, notice that the universe is getting larger and larger and larger. Not only that, but the slope is getting larger and larger. In other words, the expansion of the universe is accelerating. This was a bit of a surprise when this was discovered 20 or so years ago, but that appears to be our best guess. Of these various coloured lines, it looks like the red is the correct one. And if we follow the red back, we find the Big Bang occurred 13.8 billion years ago. We would have to amend that if our estimates of matter and energy in the universe are in fact wrong. So we believe the universe is flat and expanding according to that red line, and will go on expanding forever. So I'm not going to consider the possibility that the universe is going to come to an end at some finite time in the future. And in order to make any progress in the next few minutes, I'm going to have to change tack and change gear in terms of how fast we're running through these 10 to the power something years into the future. Instead of changing by a factor of 10 in each box, we're going to change by a factor of 1,000,000 in each box. So we've got factors of, I don't know, a zillion years, a gazillion years, I don't know what these names are. We're just going to rely on the fact that it's 10 to the power something years into the future. And the numbers are getting really, really, really big. So where did we leave the story? We left the story where we said the hydrogen was running out. If the hydrogen is running out, and stars, even long-lived stars, don't live forever. So what's the consequence? If we've got no fresh hydrogen and stars have a finite lifetime, what does that mean? There will come a day when there are no more stars shining. The age of starlight will come to an end. The stars will continue to orbit their galaxies. These are dead stars. White dwarfs, neutron stars, black holes. Dead stars in the sense that they no longer have nuclear reactions at their core, making the stars glow, producing the star shine. They might still be hot for a little while, but they'll be cooling off, and eventually there will be no more light visible. With no nuclear reactions, a white dwarf won't stay white for long. It will cool down and eventually become, well, the obvious name is a black dwarf. And the picture on the right, you can probably hardly see what's there. Let me just make it a little bit brighter. It's basically just a lump of carbon. So basically this is the fate of our sun. Once it's gone through its red giant phase, it ends up as a white dwarf. The white dwarf will cool down and it'll end up as a lump of carbon, a sphere of carbon, and that's it. A lot of stars are going to get eaten up by the supermassive black hole at the centre of the galaxy. Some might actually end up getting chucked out of the galaxy due to interactions with other stars. A lot of them are going to get eaten by the supermassive black hole at the centre. We've got some idea of how that might happen because infrared measurements taken by SOFIA, the Stratospheric Observatory for Infrared Astronomy, on a 747, has been able to map out magnetic field lines in a distant galaxy. And it's thought that matter flows into the supermassive black hole at the centre by following these magnetic field lines. In other words, the magnetic field effectively funnels matter into the supermassive black hole. I note in passing that the SOFIA is about to be retired, I presume because of the James Webb coming online and being an infrared telescope. Then I guess they figured that it's a rather expensive way of continuing to do infrared astronomy from now on. We know that atoms are made of protons and neutrons in the nucleus and electrons buzzing around. So protons are the important aspect here. They're the charged particles that are part of every atomic nucleus. Now, we don't know whether or not protons are stable or whether they decay. If protons decay, then all atoms will fall apart. Now, the timescale over which that is likely to happen is really not known. It's not likely to be before the red box indicating there about 10 to the power 36 years. So this is a long, long time into the future, and we're not sure it's ever going to happen. If it happens at this point, all atoms fall apart, all matter falls apart. Let's assume that doesn't happen for the time being. If protons don't decay, then atoms will survive a little longer. But even, for instance, black dwarfs will evaporate. It's a quantum effect I'm not going to go into. And so eventually, even if protons don't decay, then there will not be any more atoms in the universe beyond this time point of about 10 to the 42 years. Moving further into the future, we know that black holes will merge. We've seen how galaxies merging together will end up with the black holes at the center of those galaxies merging, and it's possible that supermassive black holes could grow to be not millions, not billions, but perhaps trillions of solar masses bound up in one supermassive object. But even black holes don't last forever. They are not eternal. They evaporate, providing that you wait for a really, really, really long time. So why do black holes evaporate? Well, this is again another quantum mechanical property. In quantum mechanics, it is possible to make matter and antimatter. If you like, particles and antiparticles can be created by borrowing energy and then making the matter and the antimatter. And you're allowed to do that as long as the matter and antimatter annihilate and pay back the energy on a short time scale. In other words, you can borrow energy from nothing, make matter and antimatter, which then annihilate, and bang, the energy is paid back. That, we believe, happens all the time. How is that relevant to the lifetime of a black hole? Well, you can ask yourself, as indeed Stephen Hawking did, what happens if this event happens just outside the event horizon of a black hole? Let's imagine that circle is part of a black hole event horizon. What if you borrow some energy, make two particles, or a particle and an antiparticle, one of which gets swallowed by the black hole, but the other doesn't? Now they can't annihilate, and you've ended up with the appearance of something coming out of the black hole, or at least coming from the region just above the event horizon. So there appears to be a net flux of something radiating from the event horizon of a black hole, and we call this flux of particles Hawking radiation. Hawking conjectured that it exists. We haven't proved it, but a lot of people seem to think that that is right. The radiation increases with decreasing mass. In other words, the radiation is very small for large objects, but as they get smaller and smaller and smaller, the radiation increases more and more and more. So as black holes evaporate, the radiation levels increase until it finally disappears in a flash of radiation. If we move to the extreme end of this timeline, we find that even the largest black holes, which evaporate the most slowly, even the most massive of the supermassive black holes, will eventually evaporate. But it will take trillions of times longer than the sort of black holes that we're talking about that might be stellar mass black holes. So have we reached the end of time? Well, almost. If we think about the number 10 to the power 100, which is off the right-hand end of this timeline as I've got it written at the moment, 10 to the power 100 is a googol. No, not that one. That's a misspelling of the original googol, which is 10 to the power 100. After a googol years, it is calculated that the last black hole will have evaporated. That means there is nothing left in the universe other than radiation. And therefore, from this point onwards, nothing interesting happens whatsoever. Time becomes essentially meaningless. And just to show you what a ridiculous number 10 to the power 100 is, let me just remind you what that actually looks like if you were to write it out. So remember that 6 zeros is a million, 9 zeros is a billion, that's a trillion, that's a quadrillion, quintillion, sextillion, etc. 10 to the power 100 is just a really silly number, but you can still calculate what would happen on these timescales. So, eternity, is that what we're talking about? Well, eternity is a very long time, especially towards the end, as Woody Allen once said. But in terms of trying to put it into perspective of human timescales to these ridiculous timescales, I think it was encapsulated best by XKCD, who said that a human is a system for converting dust billions of years ago into dust billions of years from now via a roundabout process which involves checking email a lot. I thought that's a wonderful way of thinking about humanity on a timescale of ridiculous numbers of years. So I don't want everybody to leave this talk feeling too depressed about the fact that everything is going to come to an end. So let me finish with a slightly more upbeat way of looking at the universe. We live in a golden age. The sun is middle-aged and well-behaved. The moon is at just the right distance to stabilise the Earth's axis and stabilise the seasons. And as a bonus, we get the spectacle of a total solar eclipse every once in a while. Thanks to evolution, we are able to explore and discover and understand the universe by, for instance, visiting our closest neighbours and building telescopes that allow us to see galaxies that are billions of light years distant. And hence we can get an idea of just how big the universe is. Mankind could not have arisen in the very early universe, as we needed lots of generations of stars to convert hydrogen into helium, into silicon, into carbon, into nitrogen, into oxygen. We needed generations of stars to make the heavier elements that were essential for life such as us to evolve. And we've just seen that the future, especially trillions of years from now, the universe looks very dark and very boring. So you could say the best time to exist is now. Thank you for listening.
That was fabulous. Thank you so much, Steve.